Platinum group. The platinum group metals are 6 noble, precious metallic elements clustered together in the periodic table. These elements are all transition metals in the D block. The 6 platinum group metals are ruthenium, rhodium, palladium, osmium, iridium, and platinum. They have similar physical and chemical properties, and tend to occur together in the same mineral deposits. However, they can be further subdivided into the iridium group platinum group elements and the palladium group platinum group elements based on their behavior in geological systems. The 3 elements above the platinum group in the periodic table are all ferromagnetic, these being the only known transition metals with this property. Naturally occurring platinum and platinum-rich alloys were known by pre-Columbian Americans for many years. Though the metal was used by pre-Columbian peoples, the first European reference to platinum appears in 1557 in the writings of the Italian humanist Julius Caesar Scaliger as a description of a mysterious metal found in Central American mines between Darien and Mexico. The name platinum is derived from the Spanish word platino, little silver, the name given to the metal by Spanish settlers in Colombia. They regarded platinum as an unwanted impurity in the silver they were mining. As of 1996, the largest applications of platinum metals were, in thousands of troy ounces/year, PD for autocatalysts, PT for jewelry, PD for electronics, PT for autocatalysts, PD for dental, RH for autocatalysts, and PD for chemical reagents. The platinum metals have many useful catalytic properties. They are highly resistant to wear and tarnish, making platinum, in particular, well suited for fine jewelry. Other distinctive properties include resistance to chemical attack, excellent high-temperature characteristics, and stable electrical properties. All these properties have been exploited for industrial applications. Generally, ultramafic and mafic igneous rocks have relatively high, and granites low, PGE trace content. Geochemically anomalous traces occur predominantly in chromium spinels and sulfides. Mafic and ultramafic igneous rocks host practically all primary PGM ore of the world. Mafic layered intrusions, including the Bushveld complex, outweigh by far all other geological settings of platinum deposits. Other economically significant PGE deposits include mafic intrusions related to flood basalts, and ultramafic complexes of the Alaska, Urals type. Typical ores for PGMs contain ca 10 grams PGM/ton ore, thus the identity of the particular mineral is unknown. Platinum can occur as a native metal, but it can also occur in various different minerals and alloys. That said, sperrylite ore is by far the most significant source of this metal. A naturally occurring platinum iridium alloy, platinidium, is found in the mineral cooperite. Platinum in a native state, often accompanied by small amounts of other platinum metals, is found in alluvial and placer deposits in Colombia, Ontario, the Ural Mountains, and in certain Western American states. Platinum is also produced commercially as a byproduct of nickel ore processing. The huge quantities of nickel ore processed makes up for the fact that platinum makes up only 2 parts per million of the ore. South Africa, with vast platinum ore deposits in the Merensky Reef of the Bushveld complex, is the world's largest producer of platinum, followed by Russia. Platinum and palladium are also mined commercially from the Stillwater Igneous Complex in Montana, USA. Leaders of primary platinum production are South Africa and Russia, followed by Canada, Zimbabwe, and USA. Osmiridium is a naturally occurring alloy of iridium and osmium found in platinum-bearing river sands in the Ural Mountains and in North and South America. Trace amounts of osmium also exist in nickel-bearing ores found in the Sudbury, Ontario region along with other platinum group metals. Even though the quantity of platinum metals found in these ores is small, the large volume of nickel ores processed makes commercial recovery possible. Metallic iridium is found with platinum and other platinum group metals in alluvial deposits. Naturally occurring iridium alloys include osmiridium and iridosmine, both of which are mixtures of iridium and osmium. It is recovered commercially as a byproduct from nickel mining and processing. Ruthenium is generally found in ores with the other platinum group metals in the Ural Mountains and in North and South America. Small but commercially important quantities are also found in pentlandite extracted from Sudbury, Ontario, and in pyroxenite deposits in South Africa. The industrial extraction of rhodium is complex, because it occurs in ores mixed with other metals such as palladium, silver, platinum, and gold. It is found in platinum ores and obtained free as a white inert metal which is very difficult to fuse. Principal sources of this element are located in South Africa, in river sands of the Ural Mountains, in North and South America, and also in the copper-nickel sulfide mining area of the Sudbury Basin region. Although the quantity at Sudbury is very small, the large amount of nickel ore processed makes rhodium recovery cost-effective. However, the annual world production in 2003 of this element is only 7 or 8 tons and there are very few rhodium minerals. Palladium is preferentially hosted in sulfide minerals, primarily in pyrrhotite. Palladium is found as a free metal and alloyed with platinum and gold with platinum group metals in placer deposits of the Ural Mountains of Eurasia, Australia, Ethiopia, South and North America. However, it is commercially produced from nickel-copper deposits found in South Africa and Ontario, Canada. The huge volume of nickel-copper ore processed makes this extraction profitable in spite of its low concentration in these ores. The production of individual platinum group metals normally starts from residues of the production of other metals with a mixture of several of those metals. Purification typically starts with the anode residues of gold, copper, or nickel production. Thus, the extraction process is very energy-intensive with environmental consequences. Classical purification methods exploit differences in chemical reactivity and solubility of several compounds of the metals under extraction. These approaches have yielded to new technologies that utilize solvent extraction. Separation begins with dissolution of the sample. If aqua regia is used, the chloride complexes are produced. Depending on the details of the process, which are often trade secrets, the individual PGMs are obtained as the following compounds: the poorly soluble 2IRCl6 and 2PTCl6, PDCl22, the volatile OSO4 and RuO4, and Cl2. Significant quantities of the three light platinum group metals ruthenium, rhodium, and palladium are formed as fission products in nuclear reactors. With escalating prices and increasing global demand, reactor-produced noble metals are emerging as an alternative source. Various reports are available on the possibility of recovering fission noble metals from spent nuclear fuel.